In this lecture, you will learn what is acceleration. You will really understand this. And if your speed is constant, do you necessarily have zero acceleration? No. And you will learn why. Then we'll talk of various types of motion, accelerated and non-accelerated, motion under gravity, and the classic example of big stone and small stone falling together from a certain height. And finally, the way graphical representation can be done of the motion, which tells a lot of information in a pictorial manner. So, welcome to the portals of real learning. Listen carefully and completely. So, last time we discussed the ideas of speed and velocity. Now, let's talk about acceleration. What is acceleration? It is the rate of change of velocity, not of speed, and it is a vector quantity. Rate of change of velocity, and that means velocity upon time. Velocity itself is meter per second. Divided by time means meter per second square. The unit is meter per second square. That means the dimension is length by time square. Therefore, m to the power 0, l to the power 1, and t to the power minus 2. And just like average velocity, average acceleration is the total change in velocity divided by the total time taken. So v2 minus v1 by t2 minus t1. v2 minus v1 is delta v, that is the change in velocity, and that's a vector divided by delta t, average acceleration. Now, when you write this as average acceleration, then it means that the direction of the average acceleration is along the direction of the change in velocity vector. It is not along the initial velocity vector. It is not along the final velocity vector. It is along the change in velocity vector. What does it mean? Suppose I have an initial velocity vector like this, and I have a final velocity vector like this. Then the change in velocity vector is this. Why? Because initial velocity plus the change is equal to the final. Initial plus change is equal to final. And by vector rule of addition, tail to head, vi plus delta v is vf. So acceleration will be along this vector. And instantaneous is again when delta t tends to 0, and then we call it dv by dt as a vector. So it is important to note that it is a rate of change of velocity, not of speed. Hence, in the case of a uniform circular motion at a constant speed, although the speed is constant, the velocity is changing. And because the velocity is changing, there is an acceleration. It is not the rate of change of speed, it is a rate of change of velocity. Right? Please note that. Now, acceleration and retardation. If the speed increases with time, then it is acceleration. That is, the magnitude of the velocity is increasing with time, then it is acceleration. If the speed decreases with time, then it is called retardation or negative acceleration or deceleration. The other various terms used. But we can combine everything and just call it acceleration. Positive acceleration means velocity, magnitude of velocity may be increasing, and negative acceleration means the magnitude of velocity may be decreasing. But then if the magnitude of the velocity is constant, even then there can be an acceleration because only the direction can be changing, just like in the case of uniform circular motion. This is very important to understand. You know, a lot of people don't really understand acceleration very well. Now, we need to make sure that we are understanding this, so pay close attention. Suppose we talk of a car that starts from rest, so the initial speed is 0, and it acquires a speed of 20 meters per second in 2 seconds. Then, what is the change in velocity? Here, it is implicit that the direction is not changing. only the magnitude is changing from 0 to 20. So the change in the velocity, magnitude of the change in velocity is 20 meters per second. And that happened in not 10 seconds, but 2 seconds. In 2 seconds. Therefore, the change in speed per second is 20 meters per second divided by the time taken to do so. That is equal to 10 meter per second. That is 10 meter per second square. That is the magnitude of the acceleration, right? Rate of change of velocity. But this is average acceleration because the time interval is not infinitesimally small. That dt should be very small. It is not small. It is average, right? Suppose the car is already moving with a speed of 25 meter per second and the brakes are applied and it stops. Finally, it stops in a time taken 5 seconds. Then the change in speed is final minus initial. Final is 0, initial is 25, so minus 25 meter per second. The change in speed or the change in the magnitude of velocity is minus 25 meter per second, which happened in 5 seconds. Therefore, per second, the change in speed is whatever is the change divided by the time taken to do so, minus 5 meter per second square. And this is retardation because the magnitude of the velocity was decreasing. So when do we have deceleration or retardation? This is very important to understand that the deceleration occurs when the direction of the acceleration vector is opposite to the velocity vector. Then the magnitude of the velocity will decrease. It's very important also to understand that if you want to ask the question that a particular body is at a particular position at a time, where will it go after a small time interval? In which direction will it go? That is decided not by the acceleration, but by the final velocity. Velocity tells us where the body is going. Acceleration only tells us what the change in velocity is going to be. It is not going to tell us the final velocity. So it only tells us the change. The new velocity is equal to the old velocity plus the change. So where it will go will depend on what was the original velocity as well. Let me give an example. Suppose you tell me that you have lost 10 rupees. You have lost 10 rupees. You had some money in your pocket and you lost 10 rupees. Can I conclude that originally you had 50 rupees or 100 rupees or 200 rupees? I cannot come to such a conclusion because I don't know what was originally the amount of money in your pocket. I only know that you lost. So the change in your money is minus 10 rupees. That is all that we know. What is the final money that you have would depend what was the original money. If you had 100 rupees, then now you have 90. If you had 50 rupees, then now you have 40. So I cannot tell whether it is 90 or 40 unless I know what was the original velocity. So if we want to know where the body is going to go next, then we need to know the acceleration as well as the original velocity. The new velocity is going to tell us where the body is going to go. Okay. Let us understand that further. It all depends on what the initial velocity is. Suppose I take a finite time interval, not infinitesimally small, so the average acceleration is delta v by delta t, and the final velocity is the initial velocity plus the change, and that's a vector equation. Suppose I take the time interval to be 1 second, then the change in velocity vector is equal to the acceleration vector because here this delta t is being taken to be 1, then delta v is going to be the acceleration. Now take case 1 that a body's initial speed is 0. U is the symbol used for initial velocity. Suppose it is 0 and there's a constant acceleration on it downwards, right? So what would be its speed? The delta v after 1 second will be equal to the acceleration, right? So delta v is equal to the acceleration, and after t equal to 1 second, the new velocity, final velocity after 1 second is going to be along the acceleration because delta v is equal to a and the delta v occurs along the direction of a. There was no initial velocity. There was no initial velocity. So whatever is the change in velocity is also equal to the final velocity. So therefore the velocity becomes like this after 1 second. What happens after another 1 second? Now it has got some velocity like this. So V1 is downwards, A is also downwards, right? So V1 and A are both downwards. So the situation is that you have the initial velocity V1 and you have a change in velocity also along the same direction. The change in velocity is along the acceleration. Both are in the same direction. So when you apply this vector equation, then it will be the final velocity will be simply a scalar sum now because the directions are the same. And it will be a larger velocity than v1. So this v2 at 2 seconds. Similarly, at 3 seconds, it will be an even larger velocity along the same direction. What do we observe? If the initial velocity was 0, then the body continues to move along the direction of the acceleration. It continues to fall down, 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 down. But if the body had an initial velocity and the acceleration is the same, then what happens? Suppose the body had a certain initial velocity perpendicular to the acceleration. So the change in velocity is going to occur along A, and this is the initial velocity, this is the change in velocity. The final velocity would, by vector rule of addition, is the diagonal of the parallelogram formed by u vector and delta v vector. So the final velocity is going to become this, the diagonal of the parallelogram. This is the velocity at the end of 1 second. After another 1 second, what happens? Now this v1 is our initial velocity. The delta v is still along the same direction. Therefore, the new velocity will be the vector sum of those two, vector sum of this vector and of this vector, which is the parallelogram formed by them. And this is the velocity now, right? What do you observe? The final velocity is changing directions. In the first case, when the initial velocity was 0, the velocity was always in the same direction. It didn't change its direction. But moment it had an initial velocity, then we find that the final velocity is changing its direction. After some more time, it is going to be like this. So the body's motion will be something like this. Starting from here, it had a velocity, but then the velocity is bending. So it's going to bend, 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 bend. It is going to follow some kind of a curve path, right? So we have to know that when you add two vectors, one is the tail to head kind of a rule, and the other is the parallelogram law of addition. The resultant of adding two vectors is the diagonal of the parallelogram. Actually, both the laws are the same thing, and we can derive that, but we're not getting into that right now. The point I want you to note is that the final velocity depends on the initial velocity and the change in velocity. That means initial velocity and the acceleration, both we need to know in order to know the final velocity. And what path it would take depends on what was the initial velocity. To further complicate matters, suppose the acceleration vector itself is changing. Here it was constant, downwards with a certain magnitude. If the acceleration vector is itself changing, then the path may be completely different, but it will follow the same rule that the final velocity in a small, infinitesimally small time interval will be the initial velocity plus the change. Okay. Now, one thing that we study very closely is acceleration due to gravity. The Earth attracts everybody and exerts a force, therefore, there is an acceleration. And on the surface of the Earth, this has got a certain value, that is 9.8 meters per second square. Earth attracts every body towards its center as per Newton's universal law of gravitation. Well, the body also attracts the Earth equally, but the Earth, which is very massive compared to the body. It doesn't move as much appreciably, and only the body moves if it is free to do so. If you look at the weight of a body, it is the force exerted by the earth on it, and this force acts toward the center of the earth, which is basically vertically downwards. The weight of any body will act vertically downwards at all times. Now, we have Newton's second law of motion, which says that F equal to ma, and therefore the weight W is mass into acceleration. Acceleration is g. G is called acceleration due to gravity, and it is the same for all objects, no matter what the mass, no matter what the velocity. This value of g does vary from place to place to a very small extent, but we usually take it as constant. On the surface of the earth, it has got a value 9.81 meter per second square. So let's go with that only. It is always vertically downwards. It is a constant acceleration. And it is the same acceleration for any body independent of the mass. So suppose I take a big rock and a small stone and drop them both from the same height. Which one will hit the ground first? Who will take less time, right? Well, I have a 10 kg mass and a 1 kg mass. Both of them are dropped from the same height. Who will hit the ground first? Well, both of them are released from rest. So initial speed of both of them is zero, right? And as we just learned, if the initial velocity is zero and acceleration is constant, then the velocity will always be along the acceleration. So velocity of both bodies will be vertically downwards at all times because the initial velocity was zero. But they have the same acceleration, g. The change in speed per second of both the bodies is the same. Therefore, the speed on landing at the ground is going to be the same. The speed at any instant of both the bodies is going to be the same. Therefore, the time taken is going to be the same. Don't think that the heavier stone will fall faster. Under gravity, every body has the same acceleration. That acceleration doesn't depend on the mass and also doesn't depend on what the velocity is. I'm talking of the acceleration, it is constant. What path is taken, that of course depends on the initial velocity. So various types of motion, we take a picture of a body every 1 second. This is the yellow one is the origin. At t equal to 0, the body was here. Then we can see it is covering equal distances in equal times. Okay. So this is uniform motion, equal distances in equal time. In this case, it is covering greater distances for successive seconds. So here the speed is increasing. Speed is increasing. That means there is an acceleration. Here, it is covering lesser and lesser distance in successive seconds. So therefore, the speed is decreasing. And still there's an acceleration, but that is a negative acceleration because the speed is decreasing. In the fourth one, it is irregular. Sometimes it is covering a large distance, sometimes small, sometimes even larger, sometimes smaller, etc. So this motion is irregular. Speed is changing, there's no doubt. But sometimes it is accelerating, sometimes it is decelerating. It is an irregular motion, right? Let's do a small question. Here's a train crossing a tunnel. Now, train has got a length. Train has got a length of 200 meters and it enters a tunnel 400 meters long. How long does the train take to cross the tunnel? It is not a point mass, it has got an extended mass, right? So the definition of time taken is this, that he is explaining the definition. From the time its engine enters the tunnel, that is the start, till the time that the last coach comes out of the tunnel, that is what he is defining as the time taken by the train to cross the tunnel. So the start t equal to 0 is when the engine is just about to enter. And this is the stop when the train has crossed, the last coach has come out. The speed of the train is given 20 meters per second. The length of the tunnel is 400 meters, right? So how do you calculate the time? We need to take a particular point and look at its displacement. If I take the engine's displacement, it goes 400 meters, right? Then it also goes another 200 meters. This is the engine. We are talking of a particular point. So the engine has covered 600 meters, and every single point on the train also covers 600 meters because the train is a train. It's not that one particle goes here, one particle goes there. So the total distance covered is 600 meters, and the speed is 20. So the time is distance by speed, 30 seconds. Let's do a question on gravity. Here, a boy has thrown up a ball up vertically, so you can see what is happening. The position is being plotted every second. So initially, look at the left side, the ball was in his hand, it was projected with some speed. After, let us say, 1 second, it is here. After another 1 second, it is here. After another 1 second, it is here. After another 1 second, it is here. And then it starts to fall down. So while going up, its speed is decreasing. And while coming down, you can see it is covering greater distances in successive seconds. So while going up, the speed is decreasing. And while going down, the speed is increasing. What is the magic here? Very simple. The acceleration is always downwards. When you threw it first, then the velocity was like this. Let us say initial velocity was like this. The acceleration vector right now is opposite to the velocity that causes a deceleration. So as long as the velocity is upwards, there is going to be a deceleration, and hence the speed decreases, ultimately becomes zero. The body stops momentarily, it doesn't stay there. It falls down. Why? Now the speed has become zero, but the acceleration is still acting. It is not stopping, right? So now it will fall down vertically. So the question is, a stone thrown up vertically rises to a maximum height of 125 meters and takes 5 seconds to do so. After that, it falls down and arrives at the point of projection. What is the distance covered? What is the total displacement? What was the average speed in the entire motion? And what was the average velocity in the entire motion? Right? So let us solve this question. Well, the total distance, it went up by 125 meters and it came down by 125 meters. So the total distance is 250 meters. What is the total displacement? Zero, because it came back to the boy's hand. The initial position and the final position are the same. This is a closed loop motion. So the average speed is total distance by total time. Distance is 250 meters and the time taken is given. Well, it took 5 seconds to go up. It will take 5 seconds to come down also. So total time is 10 seconds. Therefore, 25 meter per second was the average speed. And the average velocity was zero because the total displacement was zero. Correct? That is what happens for motion under gravity when the acceleration is constant. Let's take another question. A car is moving with a speed of 36 kilometers per hour. It then applies brakes to cause a constant retardation of 1.5 meter per second square. So that means you can say that the acceleration is minus 1.5 meter per second square. It's a negative acceleration. Now, kilometers per hour is not an SI unit, right? So we cannot do calculations, velocity being in kilometers per hour and acceleration in meter per second square. All that will lead to completely wrong answers. We need to convert everything to SI unit before we do calculations. So in fact, he's telling us to express 36 kilometers per hour in meters per second. And then he's asking, what will be the speed of the car 4 seconds after the brakes are applied? Okay, let us express kilometers per hour in meters per second. 36 kilometers per hour. Convert kilometers to meters, multiply by 1000. Convert hour to second, 60 minutes into 60 seconds. That gives me 10 meters per second. It is very important to note If you remember, this is going to be helpful to you. 36 kilometers per hour is equal to 10 meters per second. It's very helpful to remember this number. All right, so that is part A. Part B, the deceleration is minus 1.5. What does it mean? The speed reduces by 1.5 meter per second every second. Acceleration meter per second means what? It is the change in velocity per second. So when you say that the acceleration is minus 1.5 meter per second, it means that the speed is reducing from whatever value it had. The speed is going to reduce by 1.5 meter per second every second. So what is the speed of the car 4 seconds after the brakes are applied? The initial speed was 10 meters per second, right? So after 1 second, it will reduce by 1.5 meters, 8.5. What is the speed after 2 seconds? Now the speed is 8.5, reduce it by another 1.5. Like that, every 1 second you are reducing by 1.5, 1.5. So therefore, you are going to land up with 4 meter per second, right? In fact, we can write in a shorter way. Let me just rub this off. The speed at time equal to 4 seconds is the initial speed minus 4 times 1.5, because there are 4 seconds that are being elapsed and every second it is losing speed by 1.5. So in 4 seconds it will lose 6 meters per second, and therefore final speed becomes 4 meter per second. So in fact we are going to derive this formula later. Okay, is that clear? This is a very good conceptual question. Which is the correct statement out of these? A, it is possible to have an accelerated motion with uniform speed. Yes, we know that. We have seen that example. If a body is going in a circular motion at constant speed, the speed is constant, but the velocity is not constant. Therefore, there is an acceleration. Acceleration is the rate of change of velocity, not of speed. B, the magnitude of displacement can be greater than the distance. Never. Never. The distance is always greater than or equal to the magnitude of the displacement. C, the value of acceleration due to gravity g is 9.8 meter per second square everywhere. No, it varies slightly from place to place. D, a satellite moves around the Earth in a circular orbit with uniform velocity. It may be going with a uniform speed, but circular orbit, it is changing its direction always. So that is also no. Only option A is correct. Got that? Okay, some more ICSE questions. A body starts from rest and acquires a velocity of 10 meter per second in 2 seconds. So the initial velocity was 0. What was the acceleration? Well, average only, because the time interval is not small. So acceleration is the average acceleration is the change in velocity divided by the time taken to do so. Final velocity is 10 meter per second. Initial velocity is 0. Please remember, change in anything is final value minus initial value, not the reverse. It is final minus initial. So 10 by 2, 5 meter per second square. And this was positive because the change was positive. And positive acceleration means the speed increases. It did increase, right? It starts from rest and acquired a velocity of 10 meter per second. So it was increasing all the time. This is a positive acceleration. A car starting from rest acquires a velocity 180 meter per second in 0.05 hours now. Find the acceleration. Well, this is the same question as the previous one, except this hours need to be converted into seconds, right? So 0.05 hours is 0.05 into 3600. So that is 180 seconds. Well, the change in velocity is again 180 minus 0. And the time taken is 180. So it is again 1 meter per second square. Again positive because the speed was increasing. Third, a car accelerates. So this is the acceleration. Find the increase in velocity in 2 seconds. Acceleration 5 means that whatever is the speed, it will increase by 5 meters per second every second. So in 2 seconds, the speed will increase by 5 into 2, 10 meter per second. And we can mathematically show here that A is delta V by delta T. Delta V is A delta T. A is 5 and delta T is 2 seconds, 10 meter per second. Acceleration is the rate of change of velocity. Velocity is meter per second and then per second. So meter per second per second. Now we have learned about graphical representation, and it is said that a picture is worth 1,000 words. Indeed, we saw these things. If you plot displacement time graph, then ST graph for a body at rest will be a straight line, because whatever is a displacement, let us say S naught at t equal to 0, it was S naught, it remains S naught. Body is at rest. Constant velocity, we have already seen that it will be a straight line because velocity is the slope of displacement time graph. And look at this kind. Suppose you had a graph like this. Then in this part of the motion, the slope is positive, so the velocity is positive. In this part of the journey, the slope is negative because the slope is the tan of this angle, which is more than 90 degrees. That is negative. So the slope of the graph is negative. That means velocity is negative. What do you mean by positive and negative velocities? That indicates direction. Positive velocity means going this way. Negative velocity means going the other way. So it is reversing. It is changing its direction at this particular instant. Whatever is the instant shown here, the velocity is positive, it suddenly becomes negative. Okay. And we have already seen that if the displacement time graph is a curve, not a straight line, then the slope varies from point to point. That means the velocity is varying from time to time, right? And these graphs are called motion curves. So all these curves were displacement time, but we are going to look at velocity time graphs and acceleration time graphs also. Let's look at some examples of velocity time graph. Velocity is a vector, pretty much like displacement. Positive velocity means moving along plus x-axis. Negative velocity means moving along minus x-axis. We are talking of 1D motion. The velocity time graph is very versatile because it gives us two things. It gives us the acceleration and it also gives us the change in displacement. It gives us the displacement as well as acceleration. So I'll tell you how it gives us the displacement. Displacement is simply the area under the velocity time graph. And acceleration is simply the slope of the VT graph. How? We know that acceleration is delta V by delta T. That is the slope of the VT graph. So if you have a VT graph, you find the slope at any point, you have the acceleration. But displacement is very interesting. Suppose I have a velocity time graph like this. From A, it starts at t equal to 0, the velocity is 0. Then it increases and then it decreases constant, then becomes 0 at the point C, then becomes negative, then it stays constant, it again comes to 0, then becomes positive, etc., etc. Okay, that is the velocity time graph. The area under the graph tells us the change in displacement, not displacement, but it tells us the change in displacement. Now, the area above the x-axis is positive and below the x-axis is negative, right? So the net displacement, or I should say change in displacement, is the area ABC is positive, the area CDAF is negative, and the area FGHI is positive. So the net change in displacement is area ABC plus area FGHI. These are both positive, minus the area CDEF. Whatever it is, you can calculate the area. So I would like to write it once again. When you talk of the VT graph, then the slope gives acceleration. The slope of the VT graph tells us the acceleration. And the second point is area under the graph gives us the change in displacement or the change in position. Therefore, it gives us two things, and so we say it is a versatile graph. Okay. Another one, suppose velocity time graph is like this. It is a constant velocity 4 meter per second, and up till 5 seconds only it is drawn. So what is the displacement? If you go at 4 meter per second for 5 seconds, then how much is the displacement? 5 into 4, 20 meters. And that is what the area under the graph. This is the area under the graph. Okay. So 20 meters was the change in displacement. If the original position was zero, then now it will be 20 meters away. If the original position was 30 meters from the origin, now it will be 30 plus 20, 50 meters away from the origin. So the area under the VT graph tells us the change in the position. Another example is velocity itself is increasing from zero up until 80 meters per second, and this process goes on for 8 seconds, right? This is an increasing velocity at a constant rate. So what is the displacement, change in displacement rather, in 8 seconds? It is the area under the curve. Area of a triangle is half base into height. Half base is 8 seconds and height is 80 meters per second. That gives us 4 into 80, that is 360 meters. Rather, 320 meters. We are calculating the change in displacement from a velocity time graph. Suppose the velocity was 40 meters per second and then it drops steadily to zero in 4 seconds. Then the change in displacement is this area, half into the base, that is 4, into the height, that is 40. So half into 4 into 40 gives us 80 meters. That is the change in displacement, right? So these examples tell us how to find the change in displacement from a velocity time graph. Now let's look at acceleration. Acceleration is the slope of the velocity time graph. Suppose you have a velocity time graph like this, constant for some time, suddenly increasing to some other higher velocity, suddenly becoming negative and coming to this value. Then what is the acceleration? When the velocity is constant, then there's no acceleration. In these time intervals, there is no acceleration, right? But when the velocity is changing here and here, then there's an acceleration, but that is infinite. You see, the change in velocity is occurring from some value to some value, but the time taken is zero. Delta V is occurring instantaneously because acceleration is delta V by delta T. Delta V is non-zero and the delta T is supposed to be zero over here. Instantaneously it is happening. Then the acceleration will be infinite, positive and infinite. And here it is coming down to negative from some positive value to negative value instantaneously. Then the acceleration is again minus infinity, but that is not possible. No body can have an infinite acceleration because we will learn later that acceleration is caused by a force. Let us look at this. If we have a continuously varying velocity and acceleration, the velocity time graph is given here. This is in kilometers per hour and the time is in hours. And the graph is this yellow one. Suppose I ask you what was the change in displacement, then you have to calculate the area under the curve. You can see here that there are certain squares that are part of it. The value of each square is how much? Well, one side is 20 kilometers per hour and the other side is 1 hour, right? So the value of each square is 20 kilometers, right? 20 kilometers per hour into 1 hour is 20 kilometers. How many squares are there? 1, 2, 3, 4, 5, 6, 7, 8. And then some fractions, right? 8. I can say this and this constitute 1, so that is 9. Okay. I can say this and this constitute a little bit more than 1, so 10. And then this will be nearly 11. And this will be nearly 12. So total number of squares is 12 approximately, very approximately. So then the displacement is 12 squares and each square was 20 kilometers. So the change in displacement is 240 kilometers. Change in displacement is 240 kilometers. How about acceleration? Acceleration is the slope of the VT graph. So in this part, from here to here, it was a positive slope. So the acceleration is the slope, so that was a positive acceleration. At this particular point, the tangent is parallel to the x-axis. So the slope is zero. That means acceleration is zero at that particular instant. And later on, the slope becomes negative. So the acceleration goes negative. That is what we can say from this graph.